Welcome back to this course on polymer chemistry, and today we will continue our discussion on radical chain polymerization. In this lecture, I plan to cover kinetic chain length and the molecular weight of the polymer produced in radical chain polymerization, and then I will discuss several different possible chain transfer reactions and their implications in terms of molecular weight and rate of polymerization. Before I begin, just let's recap the discussion we had on radical chain polymerization in last two lectures, lecture 9 and 10. We begin our discussion with general features of chain polymerization, how chain polymerization compares with step polymerization, and then we discussed how a monomer structures determines its feasibility towards undergoing polymerization reactions towards the initiator, different kind of initiator, radical, cationic or anionic, and then we found out that during chain polymerization it is always head tail arrangement, head tail type arrangements is always exclusively preferred. We discussed different types of radical initiators, thermal initiator, photochemical initiators, redox initiator. We also discussed different types of monomers or types of monomers which can be polymerized in radical chain polymerization mechanism, and which are the types of monomers which cannot be polymerized or it will difficultly polymerized in radical chain polymerization. And we talked about that not all the radicals generated either by redox reaction or by thermal decomposition of any initiator species or by some other means actually initiate a polymer chain, part of which get lost due to some side reactions. So, the fraction of the initiators produced during the decomposition of the thermal initiator or some other process which actually initiate the radicals, we call that term as initiator efficiency. And you also discuss different steps involved in a radical chain polymerization and kinetics of radical chain polymerization, and in that way we found that dependency of polymerization rate on initiator concentration as well as dependence of polymerase rate on monomer concentration. Now, let us begin or continue our discussion on molecular weight. Molecular weight of the polymer produced in radical chain polymerization. Now, to start the discussion on molecular weight, we defined a term called kinetic chain length. Nu, which is the number of monomers polymerized per each radicals that initiated the polymer chain. We can write number of monomer that polymerized divided by the number of radicals that initiated polymer chain. Considering the time, we can say that the top one is the rate of polymerization, rate of disappearance of monomers, and the denominator is rate of formation of the radicals, which is nothing but rate of initiation reaction. So, we can write rate of polymerization divided by rate of initiation. Now, at steady state, we knew that we know by this time that R I is equals to the rate of termination. So, we can write nu as Rp, rate of polymerization by rate of termination, rate of polymerization given by Kp m dot is the concentration of all the radical species present, all the summation of the concentration of all the propagating radical, and this is Kt m dot square, or I can write simply this. Now, we know from that steady state condition where Ri is Rt, in last lecture we found that the value of m dot in case of a thermally induced polymerization is given by f k d I by k t to the power half. So, we can now write nu k p m k d k t to the power half from the last expression. What is the importance of kinetic chain length? Why we are discussing or defining a term kinetic chain length nu? We will now know that degrees of polymerization is directly proportional to nu. Exactly, we will know that average degrees of polymerization is equals to B nu, where B is the number of initiator residue, average number of initiator residue per polymer chain. So, if kinetic chain length goes up, which means number of average degrees of polymerization will go up, hence the molecular weight will also go up. So, that is the importance of kinetic chain length, that if it is goes up or goes down, then accordingly the molecular weight goes up or goes down. Now, how the molecular weight or degrees of number of average degrees of polymerization related to nu? It is twice nu if the chains or the propagating radical terminates by coupling, and it equals to nu if the termination happen by disproportionation. Now, I hope you can get this. If we just look at this, that if I have a propagating radical having a active species here, if I have a radical here at the end of a propagating chain, I have another radical at the end of the propagating chain. This has a average number of molecules nu, this also have average number of monomer molecules nu. Now, if they gets terminated by coupling reaction, the polymer which is formed here, that will have number of degrees of polymerization, or the total number of monomer present in that in the chain will be twice nu. Okay. Now, if these two propagating radical collide, interact and get terminated, or they form dead polymer by disproportional reaction, then you get two dead polymer chain, which will have again the same number of monomer molecules which were present in the chain before the termination reactions. Let us take a example, simple example, and see whether we can visualize this more. Now, let us start a reaction at T is equal to 0. I have say 1000 moles of monomer M, and say 10 moles of I initiator molecules. Now, at time t, we stop the reaction and we found that there are 400 moles of monomer still remaining. So, how many moles of monomers has reacted to form polymers is basically 600 moles of monomers reacted to form polymer chains. Okay. Now, if I consider that IT, the concentration of, or the number of moles of let us do it in the next page. At time t, we have 6 moles initiator remaining, which means 4 moles have been consumed. Each initiator molecule produces, if you consider a thermally initiated polymerization, each I produce 2 R dot. So, there are 8 moles of radicals produced during this time frame, during the polymerization reaction. Now, if say 75% of this radical has initiated a polymer chain. So, efficiency AF is 75%, that means 6 moles of radical actually initiated polymer chain. Okay, so, number of what is new? Total number of monomers polymerized, which is 600 moles, that is the number of monomers polymerized. How many number of radicals has initiated polymer chains? That is 6 moles. So, that is 100. Okay. So, 100 is the value of kinetic chain length, that means 100 monomers has in average every chain before termination, on average every chain before it undergoes termination reaction, which we call kinetic chains, has a number of monomer units of 100. So, it is clear 100 means the number of monomers on average which is present in a polymer chain before it undergoes termination reaction. We call that chain as a kinetic chain. Kinetic chain have 100 monomers. Okay. Now, what will happen, these 6 moles of there are 6 moles of chains, okay, before termination, or otherwise 6 moles of kinetic chains. Now, they will get terminated and form polymer molecules, dead polymer molecules. Let us assume that 2 moles of this become dead or underwent termination reaction by disproportionation reaction. So, how many molecules, how many chains, polymer chains? 2 moles, because each kinetic chain, two of the chain, two chains will come and react and form 2 dead chains. Okay. So, 2 moles kinetic chain will produce 2 moles. Now, rest of the 4 moles, if I consider that they undergo coupling to get terminated, then they will also form 2 moles of polymers, because each 2 mole kinetic chain will come and interact and form 1 polymer. So, they will get 4 moles of polymers. So, what is the average degrees of polymerization? Number of monomers polymerized divided by number of polymer chains, okay, because this is the total number of monomers polymerized and this is the number of chains formed. So, that will give the number of average number of monomers present in a single chain. So, that is 600 by 4, 1.5. So, that is nu is, so that is 1.5 nu, okay, which is 155 multiplied by 100, 150, 600 by 4. You can get same number if you consider how many number of we have in the mixture. In the mixture we have 2 chains or 2 moles of chains, xn bar with nu, and 2 moles of chains with xn bar of 2 nu. So, again on average you have 2 chains or 2 moles of chains with nu degrees of polymerization, 2 into 2 nu divided by total number of chains is 4. So, 1.5 nu, again you get the same number. So, fine. So, you know how the average degrees of polymerization is related to the kinetic chain length. Now, what is 1.5? If we can get this number if you consider the number of how many number of initiator residue present per chain. Now, if I have one kinetic chain like this, the one end, this end you have a one initiator residue which initiated the chain. If I react with another kinetic chain and form a dead polymer by coupling reaction, then you have a polymer chain which have 2 residues. Okay. So, a polymer formed by coupling of 2 kinetic chains will have 2 initiator residues, whereas if this undergo disproportion and form 2 different polymer chain, then each polymer will have 1 initiator residues. Okay. So, in this case this 2 moles of chain which underwent disproportionation reaction, you have total number of this has each one has 1 residues, initiator residues, and this has 2 initiator residues. You have 6 moles of kinetic chains. So, initiator residues will have 6 moles, each kinetic residues have 1 moles, and you have chains, polymer chains 4 moles. So, number of initiator residues per chain, per polymer chain is again given by 6.4 is 1.5. So, this number is nothing but the number of initiator residues per chain, which we call or term as B. Now, we can get a more general expression of B if we consider a more general example. See, if I have N is the number of kinetic chains, which means propagating radicals, and of this N, A is the fraction of these propagating radicals undergoing termination by coupling. Okay. So, total number of initiator residues in the polymer sample is N is the number of kinetic chain. So, each kinetic chain will have 1 initiator residues. So, total number of initiator residues in the sample is N, and total number of chains, polymer chains, polymer means dead chains, is A is the fraction. So, N A is the number, and if they are going termination by coupling. So, it is 2 of them produce 1 chain. So, N A will produce N A by 2 chains, and rest 1 minus A, which is undergoing termination by disproportionation, they will form 1 minus A by N chains. So, average number of initiator residues for polymer chain is given by N A by 2 plus 1 minus A in 2 by A. This is we term as B. Okay. So, if I know x n, and x n is given by B nu. So, from experiment, if I know the molecular weight of our sample, if I know the molecular weight and total amount, total gram, then we know number of chains as well, and if we get the concentration of the initiator residues, then we can divide by the number of chains to get B. Okay. So, from that we can know or experimentally determine B, and if we know B, we can find out A, or the number of fraction of chain which are undergoing termination by coupling, and 1 minus A, or the number of chains which kinetic chains which has undergone termination reaction by the disproportionation reaction. Now, in this case, we go back and see how we define the average degrees of polymerization. X n in this chain polymerization is the number of monomer polymerized by the number of polymer chain. What is the definition of X n? Is the number of monomer units present, average number of monomer units present per chain, which is obviously will given by number of monomer unit consumed or polymerized divided by number of polymer chain. Okay, simple. Now, remember in the step polymerization case, what was xn bar or average degrees of polymerization? Again it was number of monomer molecules polymerized divided by the number of molecules present at the end of the reaction. Okay. We have used that formula, number of molecules present at the end of the reaction. That means, in the step polymerization case, we have considered every molecules present at the end of the polymerization is part of the polymer sample, because there is no distinct, no boundary between, in this case chain we have monomers and high molecular polymers, there is nothing intermediate. So, we can easily remove the monomer molecules, okay, which we can discard the monomer molecules and we can only count the polymer chains. But in case of step polymerization, we are talking about number of molecules present, that means each molecules, whether it is a monomer or dimer or trimer, that also are those are also included part of polymer sample. Okay. So, when you are talking about polymer distribution, it contains the monomer, dimer, trimer type sample as well. So, in case we find in a step polymerization that our polydispersity is less than 2 in spite of having a high molecular weight, what could be the reason? We have found that in case of step polymerization, the polydispersity index is always 2, theoretical polydispersity is always 2 if we get a high enough molecular weight, because that is given by 1 plus p, p should be almost 1 to get a high molecular weight. So, ideal theoretical polydispersity index will be 2. But if you find sometime that even in spite of getting large molecular weight, our polydispersity index is lower, that could be because if we do the reaction in the solution and during the precipitation of the polymer, the monomer or the low molecular weight fractions remain in the solution. So, what we finally measuring? Measuring the polydispersity of the sample, which is devoid of the monomer, dimer, trimer, which are supposed to be part of the polymer mixture. That is the reason we might get a narrower distribution. Okay. So, that is the one fundamental difference between chain polymers and step polymers. How do we calculate, or how do you understand what the average degrees of polymerization means, or the average molecular, average number, average molecular weight is. In this case, chain case, we do not consider the monomers, whether in the step polymers case, we consider every molecule present at the end of the reaction. Okay. So, if we got this, and we can write V R P by R T or R P by R T by V. Okay. So, this is the average number of decay, we can get it from this, and unless the monomer is sterically crowded, if we are talking about a coupling reaction, then two radical chain ends has to come and collide each other. Now, unless the monomers is sterically crowded or they have a easily abstractable beta hydrogen, in majority cases they undergo termination by coupling reaction, like styrene, acrylonitrile, methyl acrylate, they are not very sterically hindered, and either they have a beta hydrogen for elimination, whereas in case of methyl methacrylate, because it has a beta hydrogen which can be easily eliminated, it undergoes termination reaction both by coupling as well as by disproportion reaction, and also we increase the temperature, the fraction of termination, fraction of disproportionation termination increases as we increase the temperature. So, till now we have been considering the termination of this propagating radical by bimolecular interaction between two propagating radical, okay, either by coupling or disproportional reaction. Now, there could be another type of reactions by which a propagating radical or a kinetic chain can get terminated, which is transfer reactions. So, now let us discuss transfer reaction. So, if I have a propagating radical Mn dot, it can react with the third molecule and form Mnx plus A dot. So, here one kinetic chain which was supposed to continue one chain is getting broken by reacting with X A and forming a new radical. Now, this new radical can initiate another chain like this. Okay. So, from one radical we have been discussing that we had one kinetic chain. In this case, from one radical we have one dead polymer plus one another kinetic chain. So, basically for a given number of monomers polymerized, the number of chains at the end of the polymerization is now more, because one kinetic chain is getting broken down to one dead polymer and another kinetic chain, which means this is a chain breaking reaction. As a result of this, the average average degrees of polymerization or the molecular weight will definitely come down. Okay. What are Xa's? Xa could be the initiator molecule, it could be the monomer itself, it could be the solvent molecule, it could be the polymer itself, or it could be any external agent which are could be added deliberately from outside, or it could be present as a impurities, and we call sometimes call as this chain transfer agent or CTA. Okay. So, let us give some examples of this transfer reaction. When Xa is initiator, say I have a reaction of acrylonitrile, it can react with, say in this case the benzoyl peroxide is the initiator, and it can take up this and form now this can again react with the monomer and initiate another kinetic chain. Okay. There could be some peroxides or hydroperoxides which also when act as a initiator, they participate in chain transfer reaction and resulting decrease of molecular weight. Example of Xa is monomer, methyl methacrylate, dot. Okay. This is not methyl methacrylate. So, this is an example of where you are getting a chain transfer by the monomer itself. Examples where Xa is solvent. See, if I take carbon tetrachloride, then it can take up a chloride and form CCl3 dot. Xa being polymer, consider polyethylene. You have another chain, okay, it could be dead chain, dead polymer. Now, it can abstract this hydrogen and form this dead chain, and you have a new polymer where you have a radical generated in between, not the end. Now, it can undergo further polymerization from here and form a chain here. Okay. So, it can undergo here and form a chain. So, you may have a branching here. So, if transfer happen within polymer, you get branching. Similarly, this can backbite, this can backbite and abstract one hydrogen from here, producing CH3 and a CH dot here. Okay. Now, this can react with monomer, giving branches. Okay. So, in this case, if the chain transfer happen with another polymer molecule, the two things happening is, one, you are getting branches, and another important thing particularly for this case is that Xn bar does not change here, no change. You have started with two polymer chain, when the transfer happened, you have same one kinetic chain and one polymer, dead polymer chain. In this case, you have one kinetic chain, intramolecular backbiting, you are resulting with one kinetic chain. Okay. So, the number of chains in this case does not change. Okay. This is a special case of chain transfer, where because of chain transfer the molecular weight does not change, okay, but it results in branching of the linear polymers. Examples of deliberately added chain transfer agent is like HAsC4H9. If we are considering a reaction with styrene, okay, again this can initiate a further chain. So, what we just now learned, we learned what are chain transfer reaction and what are the different types of chain transfer agent could be possible. It could be initiator, it could be monomer, it could be a transfer agent, it could be solvent. And in all these case, except the chain transfer to the polymers, you are generating more chains at the end of the polymerization, which means that you are breaking a chain, and as a result the molecular weight or the number of degrees of polymerization is lower than if there was no transfer reaction present. So, if I can write a general reaction like this, okay. This is the rate constant for transfer reaction and this is rate constant for the subsequent initiation and propagation reaction with the A dot molecule. So, we can write for monomer, we can write rate of transfer monomer given by K transfer monomer m dot m. For initiator, we can write similar transfer initiator K transfer initiator m dot I. Similarly, we can write for solvent CTA and so. So, in general we can write rate of chain transfer is rate constant for transfer m dot x a. Okay. Now, there could be four possibilities. This is the rate constant for the transfer reaction. Now, a propagating radical can react with a monomer which corresponds to Kp, rate of polymerization, and it can react with a transfer agent which is your rate constant for transfer reaction. And when this is new radical is formed, this initiate another new chain polymerization with a polymerization rate of rate constant Ka. Okay. Now, case 1, Ka to Kp and K transfer is much lower than the propagation. So, what is the effect on rate of polymerization? Rate of polymerization is nothing but rate of disappearance or rate of consumption of monomers. Now, if this new radical formed for transfer reaction, they also consuming monomers in the same rate, obviously rate of polymerization does not change. So, no change. What happened to molecular weight? Obviously decreased, because chain transfer always breaks a chain, and the name we gave for this type of reaction is normal chain transfer. Okay. Now, case 2 is again K is similar to Kp and K transfer is much higher than Kp. So, Rp, rate of polymerization, again no change, because the new radical form is also consuming monomer in the same rate. Molecular weight, because the number of transfer reactions, rate constant for the transfer reaction is much higher than the chain propagation reaction. So, number of chains undergoing transfer reaction is much more, okay, many more. So, the molecular weight drop significantly, okay, it is large decrease in the molecular weight, and we call this as telomerization. The third case is Ka, the new rate of polymerization with the radical formed due to transfer reaction is lower than Kp, but rate of transfer rate constant for transfer reaction is much lower than the rate constant for the original polymerization reaction. In this case, because this rate is lower, then chain polymerization rate of polymerization will come down, so as the molecular weight, and we call this as retardation. Now, there is fourth case, that is the worst case, where K is lower than Kp and K transfer is higher than Kp. Okay, in this case, because of this rate comes down, and because of this the molecular weight is large drop. So, both large decrease in the molecular weight as well as the large decrease in the rate of polymerization, and this we term as degradative chain transfer. Here basically at the in the reaction you get extremely low molecular weight polymers or oligomers, and that too the rate of consumption, rate of reaction of the monomers happen much lower. In this case, in the telomerization case, rate of polymerization is fast, the monomers reacted much at the same rate as if there was no transfer reaction, but the molecular weight drops. So, for a given time you are getting yield number of polymers you are getting more, but the rate at which polymers monomers is reacting is similar as the original rate, but the molecular weight drops significantly. Okay. So, we now write the kinetic expressions. Now, we have found that this is the expression gives the average degrees of polymerization without any transfer reaction, where only the termination is due to either coupling or disproportionation, and B is the average number of initiator residues per polymer chain at the end of the reaction. So, if we talk about transfer reaction, we have to include the other reactions by which termination takes place, which are other rates of transfer by the monomer, rate of transfer by initiator, rate of transfer by solvent, or rate of transfer by the CTA, chain transfer agent. Now, we are not writing rate of transfer by polymers, because as we have seen that polymers they do not contribute in terms of decreasing the number of molecular weight of the polymers. Okay. So, we are not considering the rate for chain transfer in polymers case. Okay. So, if I can write 1 over x bar, I can write R T by B by R P, similarly R transfer by R P, and so on other terms. Okay. Now, this is 1 over x n 0, which means the number average degrees of polymerization in absence of any transfer reaction, and you can write the rate expression for individual rates. So, K transfer is given by rate constant transfer monomer m dot m by K p m dot m, plus if I talk about the initiator, then K transfer initiator m dot I K p m dot m plus others. Okay. 1 over x n 0 m by K p plus K transfer I by Kp I by m, so on. Okay. Now, this is the rate of transfer, rate constant for transfer by the original rate of propagation is we are writing transfer coefficient or transfer constant. So, this is the transfer constant for chain transfer constant for monomer, this is chain transfer constant for the initiator. Similarly, for solvent we can write Cs solvent by m plus C CTA by m. Okay. Now, this is Mayo equation. So, any increase in the right hand side, anything which increases the value of the right hand side will decrease the molecular weight. Okay. So, in any absence of any transfer reaction, you get the highest molecular weight, which is basically the molecular weight we get in absence of transfer reactions. Now, just look at this transfer reaction once. Now, typically in normal cases, the transfer to monomer and initiator are very negligible. Okay. They generally do not take place, and unless we add a transfer agent from outside deliberately or the impurity is present, this also does not contribute too much. So, actually the main contribution for chain transfer agents, chain transfer reaction is the solvent. Okay. So, whether this might be significant for some particular cases, but this is very important for in the majority of the radical chain polymerization reactions. Okay. So, let us discuss little more about this term Cs and so basically for a given concentration of monomer and solvent, this is the Cs, the value of Cs will determine the chain transfer reactions in terms which will determine the value of the molecular weight of the chains getting produced in these reactions. Now, if I go by and look this Mn chain 1 propagating radical, they can react with a monomer which is Kp, and it can react with Sxa, which could be solvent and others, which is basically the transfer. Now, this produces again Mn bar, Mn 1 plus, if you can write, and this produce A bar plus X Mn x. Okay. Now, whether a chain transfer will happen, and if it is happen, how extent, it will determine by the reactivity comparison between the monomer and the chain transfer agent or the solvent here, and also the stability of this Mn dot or A dot. If it is more stable, then it will be, this reaction will be dominating over the original propagating reaction. If it is this Mn dot, which is the original propagating radical, is more stable, then obviously this will be more preferred reaction over transfer reaction. If the reactivity of the original radical, propagating radical, is very high, then it can not distinguish in that extent. In other words, even if there is a difference in the reactivity of these two molecules towards this, because this is highly reactive, it will react both M and this. If it is less reactive, then the more reactive between these two, it react with this. Okay. If it is very reactive, then both will react. Okay. If it is less reactive, then between these two, which is more reactive, that will react with this. So, that reaction will be prominent, preferred. Let us take few example and see whether we can grasp this. Okay. Let us consider examples like benzene. We are talking about solvent. Let us consider XA as solvent. So, benzene, cyclohexane, toluene, ethyl benzene, isopropyl benzene and tertiary butyl benzene. Okay. Now, if it has to react with Mn dot and undergo a transfer reaction, obviously, this is the hydrogen which will abstract, this is the hydrogen it will extract from here, and between, in this case, this is the hydrogen is more easily abstractable, and in this case it is this hydrogen it is abstractable, and this case this hydrogen it is abstractable, and this case there is no hydrogen here. So, this hydrogen which is more extractable. So, what is the resulting radicals formed in this case? This radical, dot, okay. Now, from your basic knowledge of organic chemistry, you know what is the order of stability of this radical. Okay. Now, the more stable the radical is, it will participate in the transfer reaction in more extent. The lower is the, if it is lower, then it will participate in the transfer reaction in lower extent. So, what is the value? If I, so what we will do in the next lecture, let us start from this page and look at the value of this Cs, transfer constant, and as you know, the higher the value of Cs, the more the solvent participate in the transfer reaction. So, lower would be the molecular weight of the resulting polymer. So, let us stop for this class this lecture now, and we will start from this page in the next lecture immediately.